Hello, this is Trude Socrates. Welcome to a portrait of linear algebra. Today's video is about orthogonal complements and orthogonal decompositions. So you're probably thinking, I've heard those terms before. And of course, we saw this in chapter 2 when we talked about the dot product and we talked about orthogonal complements. And remember, that was the only time when we assembled the basis vectors for a subspace into rows of a matrix instead of columns, and we found the null space. We also saw this idea in chapter 3 when we talked about the projection of a vector onto a plane and onto its normal line. So let's take a review of that. This is basically the idea. Okay, so if you have any vector in R3, you can write it as a sum of a vector, let's say, on the x-axis and on the yz plane. Okay, so those two subspaces are orthogonal complements of each other. Okay, the x-axis is perpendicular to the yz plane. And we generalize this for any line through the origin and its orthogonal complement, which is the plane through the origin with that normal line. Right? So in today's video, we will learn that in any inner product space V, not just in Rn, we can generalize the definition of the orthogonal complement W per of a subspace W of V. We will show that the dimensions of W and W per add up to the dimension of the ambient space when that ambient space is finite dimensional. So remember, this is true in Rn. A plane is two-dimensional. A line is one-dimensional. 2 plus 1 adds up to 3. Okay? And we will also learn how to construct what's called the orthogonal decomposition, V equals W1 plus W2, of any vector V in your ambient space, where the first vector is from W and the second vector is from W. All right, so here's the definition for the orthogonal complement of subspace W of an inner product space V. It is just the set of all vectors V in the ambient space, so that the inner product of V with W is 0 for every vector W in our subspace. One of the first simplifications that we did in chapter 2 was, well, we don't have to focus on every vector in our subspace. We only have to do it for every vector in some basis for our subspace W. Okay? So a vector V in the ambient space is a member of the orthogonal complement if and only if its inner product with each and every one of these basis vectors is 0. Okay? All we have to do is check that our vector is orthogonal to each and every one of these k vectors. Okay, now why is that so? Instead of having to check with every W in our subspace, well, we have a basis V for our subspace, so therefore W can be expressed as a unique linear combination of W1 through WK. There it is. Okay, then what do we have to do? Well, we want to check that it's enough that the inner product of V is 0 for every one of these basis vectors. So suppose that V inner product with W1 is 0. So we are orthogonal to first vector. And we are orthogonal to all of the vectors. Okay, so inner product with W2 equals 0, and so on. Okay, so now let's check. Are you also going to be orthogonal to every vector in our subspace? Okay, so under this setup, we can now take the inner product. We will get the inner product of V with W will be, and this should feel familiar to you, right? We did this, or this idea at least, in our previous video, okay? So replace W with this linear combination. What are the two magic properties? Additivity and homogeneity, okay? So I think that we have grown up enough that we can do those two steps together, shall we? So C1 goes out, and we have only W1, okay? Repeat with C2, and we only have the inner product of V with W2. So I will erase these and these, okay? So you see it taking shape right before your very eyes. So the last term is going to be the inner product of V only with WK. All right, so we combine additivity, homogeneity, two steps, and we can simplify this inner product. Okay, all of these are 0, so of course that simply adds up to 0. And so V is orthogonal not just to the basis vectors, but to every vector in our sites. All right, there is one more special property of the orthogonal complement that I want to point out because we're going to need it later when we do the orthogonal decompositions. Suppose that W is any subspace of an inner product space V with orthogonal complement W per, then the intersection of W and its complement is only the 0 vector. Okay? The only vector in common to W and W per is the 0 vector. We saw this in R2 and in R3. All right? In R2, you have a line through the origin, and its complement is the perpendicular line. So they only have the origin in common. In R3, what did we say? Plane through the origin, normal line through the origin. What do they have in common? Just the origin. Okay? So it's going to be true in general for any subspace, in any inner product space. Okay, so how do we do this? Well, it's usually almost the same idea, right? Pick somebody in the intersection, show that there's only one somebody in that intersection, the 0 vector. Okay, so W is in the intersection of W and W per. Okay, so this means that W is from W, our subspace, and it also means that W is from the complement. Okay, it is both from the subspace and the complement. All right, but what's the meaning of the complement? The complement is every vector in the ambient space, which is orthogonal to every vector in the subspace, W. Okay, so what does that mean? It means that the inner product of W with itself has to be 0. Okay, so by the definition of W per, this means that the inner product of W with itself is 0. Okay, well, who are the vectors in an inner product space whose inner product with itself is 0? Well, we have the non-degeneracy property. So W has to be the one and only 0 vector. By the non-degeneracy or positivity property, it has two names, W has to be the 0 vector. Okay, so therefore, the only vector in the intersection has to be the 0 vector. Okay, we only have one more theorem to go before I give you an example. Okay, so I apologize if it's theorem. Okay, just 5 more minutes, I hope. All right, so what we're going to do next is generalize the dimension theorem from chapter 2, which was the dimension of W plus the dimension of W per is n, where W is a subspace of Rn. Okay? We're going to do this now for any inner product space, so we don't have to be in Rn anymore. Okay? We're going to use the Gram Schmidt algorithm. So what we will need in particular is this very special property of the output vectors in Gram Schmidt, and that was the preservations of spans. I hope you remember this. It's right here. Okay? Remember that the input vectors are the W's. The preliminary output vectors are the V's. Okay? But the final output vectors, which we call the U's, they're just the unit vectors corresponding to the V's. Okay? So the Gram Schmidt algorithm was rigged so that the span of the first input vector is the same span as the first output vector, preliminary output vector. Okay? But U1 is just V1 divided by its length. So really, it's the span of the first final output vector. Okay? Similarly, if you take the first two input vectors, they have the same span as the first two final output vectors. Okay, so again, we can replace the V's with the U's. Same thing for the first three vectors. The span of W1 through W3 is the same as the span of U1, U2, and U3, where those are our first three final output vectors. Okay, so keep this in mind as we state the dimension theorem for orthogonal complements. Suppose that W is a k-dimensional subspace of an n-dimensional inner subspace, inner product space, V. Okay? Suppose that W1 through Wk is a basis for W. Okay, so that should start matching with our notation here. Okay? We can enlarge B to B prime, a basis for V. Okay, so now we will have Wk plus 1 through Wn added on to W1 through Wk. Okay, so I hope you remember what allows us to do that. It's called the extension theorem. All right, so pick any Wk plus 1 not in the span of W1 through Wk, and then pick Wk plus 2 not in the span of W1 through Wk plus 1, and so on. Okay, so let's just say you have a 5-dimensional inner product space. Okay, start with a 3-dimensional subspace of that inner product space. Okay, pick a fourth, make a basis first for W. So W1, W2, W3. We know we can do that. And then pick a fourth vector not in their span. Okay, great. Now pick a fifth vector not in their span. And we know, of course, we can do that because V itself is 5-dimensional. Okay, so we can do the extension theorem in 2 steps. Okay, take as many steps as you need until you get n vectors, which will be a basis for V. Okay, so what do we do next? We will apply the Gram Schmidt algorithm to this final basis for V. And we will get us our outputs, U1 all the way to UN. Okay? So, what are we going to do now? There you go. I might as well show you the whole theorem. There it is. Okay? So we will separate S, partition S, into 2 subsets. U1 through UK, the first k vectors, and then the rest, UK plus 1 to UN. So there are n minus k vectors in the set. Okay? Well, what does preservation of subspaces say? Now, the span of the first 3 vectors in the output is the same as the span of the first 3 vectors in the input. So, the span of the first k vectors in the output is the span of the first k vectors in the input. But wait a minute, that's a basis for W. So therefore, S1 is also a basis for W, but because the output is an orthonormal set, it's an orthonormal basis for W, even more special. What about these other vectors? Oh, they must be an orthonormal basis for the orthogonal complement. Ha! So, consequently, the dimensions of W and its complement have to add up to N, the dimension of our ambient space. Now, there's a generalization for this. Okay? Suppose now that you have that S is any orthonormal basis for V. Okay? So, start out with a complete basis for V, and it's an orthonormal basis. Okay? Now separate them into two sets with no member in common. Okay, so we partition them. Okay, the three of you go over here, the two of you go over here. Okay? Well, if you make W1 the span of the first set and W2 the span of the second set, they have to be orthogonal complements of each other. Okay? So this means that the orthogonal complement of the orthogonal complement must be the original subspace W. Okay? So most of what's being said in this theorem we already know to be true. Okay? The first set is definitely a basis for W because of the preservation of spans property that we mentioned. Okay? So it's really S2 that is a mystery. Okay? Why is it that S2 is a basis for the orthogonal complement? Okay, so here's the setup. We want to look for all the vectors in our ambient space, V, which are orthogonal to every vector in W1 through Wk, which is our basis for W. But we can also do it for every vector U1 through Uk, because that is another basis for W. Okay, so here is a generic member of our vector space. We know it can be written as a linear combination of our final basis vectors, U1 through Un. Okay, so what do we have to do? We want V to be orthogonal to U1 through Uk, right? Because U1 through Uk, we already know, is also a basis for W, and it's not just any basis, it's an orthonormal basis for W. Okay? So therefore, we want the inner product, magic, of V with U1 to be 0. Okay? However, what is the inner product of V with U1? Well, V is over here. Replace. Okay, well, you know what's going to happen next, right? We're going to have additivity followed by homogeneity. Okay, so what are we going to get? First term, we will have only C1, and then we will have the inner product of U1 with U1. So I will erase everything except for U1. Okay, what's next? C2, and this time inner product only of U2 with U1. So that goes away. They all go away except for U2. Okay, so keep going. Let's stop at UK, and then you take away everything but UK. Keep going. There's more. CK plus 1. Take everything away except UK plus 1. And finally, up to UN, up to CN, and then, why don't I just do this? take everything away except u. Okay, there we go. But what do we know? All of these u's are orthogonal to each other, and they're unit vectors. Okay, so what's going to happen? That's 0, that's 0. All of these are 0, except for this one. So the only survivor, boom, is C1. Oh, look, C1 has to be 0. Okay, that might also sound familiar to you. It's almost like we're doing a dependence test equation, doesn't it? Except no. This C1 is from this vector V, which is from our ambient space. Okay, so it would be good if that felt familiar to you, but it's a slightly different scenario. So now, we will update. V must look like, V is this enormous linear combination, except there is no U1, because C1 is 0. Okay, so now what are we going to do? I give you one guess. Repeat for U2. Okay, repeat. Take the inner product with U2. Okay, so what's going to happen? So this will be a U2. So there's no U1, so that term is gone. You'll get U2, U2, up to UK, U2, UK plus 1, U2. Everything on the right is going to be U2. So the only survivor will be U2, U2, which is 1. So we get C2 must be 0. This will get us C2 equals 0. Okay, now we have to be careful where we're going to stop. Okay? We can go as far as CK. Alright, so there will be no terms to the left of CK. And then we'll take the inner product with UK. Alright, so the right vector, all of those will now be UK. Alright, so UK will still be orthogonal to UK plus 1 through UN. So the conclusion that we'll get is our CK is 0. Okay, keep going up to UK. This will get us all of these coefficients, C1 through CK. C2 all the way to CK. Those should all have to be 0. Okay, so let's take a little pause here. Okay, where are we now? All the coefficients up to CK have to be 0. Okay, so thus V has to look like this linear combination, except it starts at CK plus 1, UK plus 1. Okay, but now let's double check. Is V in our orthogonal complement? Is V in, where's my elements? There you are. Is V already in W? Okay, so we're going to play the same game. Okay, we will take the inner product of V with U1. Okay, take the inner product of V with U1. Okay, are we really done? Let's check. U1 is orthogonal to UK plus 1 all the way to UN. Yes, that's done. Okay, is it orthogonal to U2? Well, U2 is orthogonal to UK plus 1 here. Yes, so they are all equal to 0. Yes, V is orthogonal to U1 through UK. So there we go. We've done our job. By making all of these coefficients from U1 to UK equal to 0, what we have left is guaranteed to be a member of the complement. Okay, but, oh, wait a minute. Who are these vectors? Haha. Those are exactly the vectors in what we call S2. Okay, so therefore, S2 spans the complement, and it's an orthonormal set, so it is also automatically linearly independent. Spanning, independence, basis. There you go. That's the end of the proof. Thus, S2 spans W perp, and since S2 is orthonormal, it's linearly independent. Okay, and so S2 is an orthonormal basis for the orthogonal. Alright, so before we do our example, let me just say that that last line in the theorem, it's not true for infinite dimensional inner product spaces, okay? That the complement of the complement is the original subspaces, okay? So infinite dimensional vector spaces are always trouble, okay? And that's why they don't really belong in linear algebra. Okay? They belong to a field of mathematics which is often called functional analysis. Okay? Because most of the infinite dimensional vector spaces that we love and are interested in are function spaces. Okay? So therefore, in functional analysis, we extend the ideas of linear algebra into these infinite dimensional vector spaces. Okay? However, it is always true that the original subspace is inside the complement of its complement. Okay? And that's a fun exercise. It basically makes you unravel the definition. What the hell does W perp mean? Okay, so let's get on with our example, which we will recycle, extend from our last video. Okay, so at the last part, we implemented the Gram Schmidt algorithm on these 4 input vectors. It took us about 20 minutes, I think. And the final output was these 4 unit vectors. And of course, they're mutually perpendicular to each other. Okay, let's take a look at the second and the fourth. What's the dot product? We got 4 plus 4, 8, minus 6 is 2, minus 2 is 0. Okay, so of course, any pair of these vectors are orthogonal to each other. Okay, what are we going to do? We will construct 2 subspaces. Okay, I will give you 2 examples for the price of 1. Suppose that W is the span of the first 2 input vectors, and suppose that U is the span of the first 3 output vectors. Okay, can we make another one? Let's say W2, W3 only? I'm afraid not. Okay, and that is because of the preservation of subspaces of spans property. Okay, notice that they always start at W1. W1, W1, W2, W1, W2, W3, never W2, W3. You have to start at W1. Okay? So if you're interested in W2, W3, I'm afraid you're going to have to start over. What does that mean? Put W1 at the end of the list, maybe, and then apply Gram Schmidt algorithm again, one more time. Okay? So we are kind of constrained to these 2 examples. Okay, so what are we going to do? Find an orthonormal basis for their complements. Okay, that's it. Okay, well, this is not a very difficult problem. Okay, let's go back to the theorem. Theorem said, if you have already made this basis for the ambient space, in our case it's R4, and you partition into these two sets, okay, then the first is an orthonormal basis for the subspace W. The second is an orthonormal basis for the orthogonal complement. Okay, so we can apply that idea to these two subspaces. Okay, one at a time, of course. So in W, we have W1 and W2. So U1 and U2 will be in our S1. U3 and U4 will be in our S2. Okay, so therefore, I need the perp symbol. Here we go. I'll borrow it here. So W perp has orthonormal basis. All we have to do is copy U3 and U4. That's it. We have done the hard work when we did the Gram Schmidt algorithm. There you go. That's it. That's all you have to do. So similarly, what is it for U perp? So this time it is U perp. U perp has orthonormal basis. Okay, so for U, we want the first three vectors. So that will be our S1. I'm sorry, this will be our S1. Our S2 will just be made of U4. So all I have to do is harvest that last vector. That's all there is to it. All right, before you celebrate though, there is one more thing that we have to do, and that is to construct orthogonal decompositions. Okay, so suppose that W is a finite dimensional subspace of an inner product space V. Okay, so I did not say that V itself is finite dimensional. No, only the subspace has to be finite dimensional. Okay, but of course in our examples, the ambient space will also be finite dimensional. Then, any vector V from our ambient space can be expressed uniquely as a sum. V is W1 plus W2, where W1 is from the subspace W, and W2 is from its orthogonal complement. We refer to this equation as the orthogonal decomposition of V with respect to W and W perp. Moreover, we can explicitly construct W1 and W2 as follows. Suppose that U1 through UK is any orthonormal basis for W. Okay, and this is why it's only important for W to be finite dimensional. Then W1 will be the inner product of V with U1 times U1 plus the inner product of V with U2 times U2, and so on, up to the inner product of V with the last basis vector UK times that basis vector UK. How do we get W2? Arithmetic. Simply subtract W1 from V. So obviously, if you add W1 to W2, W1 will cancel out and leave you with V. Okay? So we call W1 the orthogonal projection of V onto W, and W2 as the orthogonal projection of V onto the complement W perp. So symbolically, that's proj W of V and proj W perp of V. Okay, so why does this work? It's basically, again, just the same idea as what we did over and over. Okay, we already know that if this were actually a basis for the entire space, okay, these coefficients are exactly the coefficients that you need in order to create the vector, okay? So we only need a minor adjustment to that idea to create this orthogonal decomposition. Okay, so this is what it looks like in R2. If you have a line and its perpendicular line goes through the origin, then the orthogonal decomposition of a random vector is just like your right triangle vector diagram. Okay, so try to make a right triangle with the sides parallel to W and its complement. That's your orthogonal decomposition. Okay, so here's the generalization where you have an ambient space which doesn't have to be Rn, okay, and you have a subspace and its orthogonal complement. Okay, so by the way, let's talk about uniqueness. Okay, why is the decomposition unique? Okay, so the formula I leave up to you to see why it works. But why is it that there's only one way now to make this orthogonal decomposition? Okay, so suppose you had two ways to do it. Okay, so instead of just W1 plus W2, let's call them W1 prime plus W2 prime. Okay, so we want to ask, okay, is there really a second way to do it? Okay, so what are we going to do? Magic. As usual, it's magic. There are two ways to do this, so these two have to be the same. Well, what are we going to do? Let's put W1 together with W1 prime. Okay, so let's make W1 prime move over to the left to join W1, and then we will evict W2 and say, you know, you go to the other side. We don't want you here. W2 prime minus W2. Okay. Why is this so important? Why does this tell us everything? Well, W1, remember, where are these vectors from? W1 is from W, and W2 is from W per. Okay, but now, they are both subspaces. Okay, so by closure, the left side is in W, and the right side is from the complement. Okay, but they're equal to each other. The same vector is in W and in W per. Okay, what was that last theorem that we saw in the introduction? The only vector in common to W and its complement is the zero vector. That's why it's so important. Since the only vector common to both is 0v, whoops, wrong symbol, 0v, we must have the first vector is 0, so is the second vector, because they're the same vector. So they both have to be the 0 vector. Ooh, what does that mean? W1 must be W1 prime, W2 must be W2 prime. So there is only one orthogonal decomposition. All right, so let's build on our last example. We have these 4 input vectors for R4 into the Gram Schmidt, and these are the 4 final output unit vectors. We made these 2 subspaces. We made a basis for the complement W perp and the complement U perp. Okay, so now we are going to find the orthogonal complement or orthogonal decomposition of this vector in each case for each of these subspaces. Now, I apologize that the traditional notation for the orthogonal decomposition uses W1 and W2. Those are the same symbols that we have for the input vectors in the Gram Schmidt algorithm. Okay, so if that confuses you, let's just pick a different flag. There you go, x1 and x2. So we would need v minus x1. Okay, so let's use that for the first, and then let's use a different letter for the second. Okay, all right. So the formula said just use as your coefficients the inner product, which is in this case is the dot product of the first two vectors in our output set. Okay, those will be the coefficients for these two vectors that will make up our x1. Okay, so let's do that. Let's put that over here. Make a copy here. Okay, so in this case, the inner product is just the dot product, so let's change notation. Let's make that the dot product. There you go. Okay, and the same thing for the second one. Let's turn this into dot product, where that is. Okay, so what is the dot product of this vector with u1? Okay, we got 4 plus 5 is 9, 0, 9 minus 2 is 7. Okay, 7 times u1. Okay, so let me spell it out. 7u1 plus, okay, so now take the dot product would be 2. 8 minus 20, negative 12, minus 21, negative 33, minus 4, negative 37. So minus 37 times 2. Okay, however, when we take the dot product, the norms are part of u1. So it's not just 7. It is 7 over radical 3 u1. Okay, do not forget the denominator. And similarly, you need minus 37 over square root of 33 u2. Okay, those radicals are important. Okay, so let's see. We are going to get 7 over rad 3 times this entire bracket minus 37 over rad 33 times this unit vector. Okay, so you see what's going to happen. Those square roots are important because they will neutralize these square roots that appear in u1 and u2. So that's no longer square root of 3, that's just 3. That's no longer square root of 33, that's just 33. Okay, so that should be our x1. Maple, could you do that for us? Yeah, sure. Ooh, it simplifies a little bit. Okay, great. So according to the formula, x2, you just take the difference. Okay, so x2 is v minus x1. Our v is this guy over here. And we subtract this one. Okay, there you go. So that's the orthogonal decomposition. If you add these two together, you should get the original vector. Okay, and of course you better because we just used maple to take the difference. Okay, but more importantly, we should check orthogonality. Okay, so the basis property tells us that the first vector has to be from the subspace because we have basis here. But why is the second vector from the complement? Okay, so take the dot product. If you take the dot product, you will get 43 from the first, minus 75 times 20 in the second. Make sure you have the same denominators here and here. Okay, so sometimes Maple simplifies. Plus 37 times 40, and then minus 23. Maple, is that 0? Yep, that's 0. Okay, so our x2 really is in the orthogonal complement. Okay, so let's do the same now for the second subspace. Okay, so if we were to follow the recipe, let's do it here. Okay, all we have to do is add one more vector. Take the inner product with u3 times u3. Okay, but why should we do that? I mean, you know, in fairness, all we have to do is compute one more term, right? Okay, but let's do something different. Okay, instead of solving for x1, let's call it y1 now and y2 for our second subspace. Okay, why don't we do y2 first? Okay, pretend now that it is the okay, so big picture. Why can we do? Okay, before I do the magic, okay, let me explain that first. Why is it that we can do y2 first? Okay, that's because when we did our last example, the previous one, we said an orthonormal basis for u perp is just the fourth unit vector in our output. Okay, remember there was just one vector and it was this guy. Okay, so this is an orthonormal basis for u perp. I'll just start it. Okay, so this allows us now to find y2 directly. Okay, same formula. Take the dot product of these two vectors. 8 minus 5 is 3, plus 14 is 17, plus 2, 19. Okay, so that is 19 over square root of 10 times this vector. Whoops, wrong times. That should be that times. Okay, there you go. Okay, but of course, that melts the square root of 10. So we just said, that's it. That should be our y2. Okay, but now, now we need y1. So y1 will be the same vector v, down here please, minus y2. Okay, that's what we get. Ooh, what did I tell you? See what it did? Ah, sneaky you. Some of them are 10s, some of them are 5s. Okay, so when we check, those denominators will give us a problem. So that should be a 2 over 10, and that should be a minus 32 over 10. Okay, I'm glad this happened. Okay, it can happen to you. So now, when you take the dot product with the first vector, do we need the 19 over 10? Not really. It's just a scalar movable. Okay, so now what do you get? 4 minus 69 plus 32 times 2, 64. Ooh, plus 1. Okay, what happens? Negative 69 plus 64, negative 5 plus 4 plus 1, that gives you. Okay, so therefore they are orthogonal to each other. Okay, and of course, you want to check they add up together? Fine. Take this and add the second one. And of course, we're going to get the original vector. Okay, there we go. So that is those are our two orthogonal decompositions. Thank you very much. This is our second to the last video. So one more video to go. We're almost at the end of our class. Thank you for watching this video. I hope you enjoyed it. And until our next video, enjoy the rest of it. Bye.